Now, how you could define that two sets like A and B are equal? Again, it's not like the normal equality we use in math where we have 1 equal 1. No, it will be similarity, which means does the first set contains all elements and those elements are contained in the second set. So basically a set equality, two sets are equal if and only if. Okay, and if and only if now it's really important to focus on. They have the same elements. So the same elements are both exist in both sets. So if A and B are sets, then A and B are equal if and only if there is X. Okay? For all X now, there is one X belongs to A if and only if X as well belongs to B. So we could write A equal B if and only if A and B are equal sets. Based on the definition, we can see here that the first set, which is A, contains the element 1, contains the 3, 5. Now the second set as well contains the 3, 5, and 1. Now look to the second example. The first set A has the element 1, 5, 3, 3, 1, and the second one is 1, 3, and 5. Are they equal? Yes. Because basically here, both elements are satisfying the relationship. So 1 belongs to A if and only if 1 belongs to B. 3 belongs to A if and only if belongs to B. 5 belongs to A if and only if belongs to B.
So it could.
Now what we mean by subsets? There is a set called A, and it will be a subset of the set capital B if and only if every element now of A is also an element of B. But this is not necessarily means that the elements of B should exist in A. This means the set B could have more elements than the set A, and still set A is a subset of set B. So the notion A capital is a subset of B is used to indicate the subset relationship, and A is a subset of B holds exactly when they have if and only if there is an X which basically belongs to A, then belongs to B. Now here we are not doing if and only if, and the reason why we do this, because it might be possible that there is an element called X and this X belongs to B, but it does not belong to A. And this is why we have use the relationship if then, not if only if. If we say if only if, so this definition will be an equality. It will not be a subset definition. So because an element like small a belongs to the set phi, which is always false, phi is also a subset of big S for every set of S. And this is what we say, the empty set is an element of every other set. Because A belongs to capital S, then A belongs to S, then S is a subset of S. The same set could be a subset of itself for every set of S, which is basically satisfy the condition. We satisfy the first part, which is if then. If S is a subset, then S is a subset of S. You could show that a set is not a subset of another set by saying A is a subset of B. You need to have one X which belongs to A, then the same X is also belongs to B. Now, to show that A is not a subset of B, you can just do that when you find one element in A, one element in A, where basically the same element does not exist in B. So for example, the set of all computer science majors at your school is a subset of all students at your school. That's a true one. Now the set of integers with the squares less than 100 is not a subset of the set of non-negative integer. That's a false one. You could also look to equality in sets by saying A equal B if and only if there is X where X belongs to A, if and only if X belongs to B. And you can use logical equivalence, the same one we covered in the previous week, where we say for all of X, there is X belongs to A, then X belongs to B, and this could be translated to and X belongs to B, then X belongs to A. Now if you do this, use the same logical equivalence law for the relationship of subset, you cannot end up with this and relationship. So here you have to satisfy the condition that X is an element of A, then X is an element of B, and also X is an element of B, then there is an X element of A. So if we have A, which is a subset of B, but A is not equal to B, then we say that A is a proper subset of B, and we denote it by the notation A proper subset of B. And then for all of X, now the relationship is different, because here for all of X there is an X belongs to A, then it belongs to B. Now the only exception we have, and there is one X, there is one small X in B, and it's not in A. But you can just simplify it using Venn diagram, where you have the universal set U, the big square you can see here in the diagram, and you have a small subset of B called A, and there is as well the set B. Now this is a proper set of B. A here is a proper subset of the big set B. But it's not covering all the elements. It just covers a small portion of the big set. So we can also use cardinality relationship as an operation over sets. So if there is exactly an n distinct element in any set like S, where we have a definition for n as a non-negative integer, we say that S is finite, otherwise it is infinite. Now, the cardinality of a finite set like A, denoted by the absolute value of A, is the number of distinct elements of A. And this is where you remove duplication from the finite set. And that's why in databases, in SQL, in MySQL, or in any database implemented in computer science, we always deal with finite number of sets, because we don't like duplication. We try to get rid from duplication. We try to do normalization to remove all the duplicate values in any table. So for example, the cardinality of the empty set is 0. The cardinality of the set 1, 2, 3 is basically 3. The cardinality of phi equal 1, and the set of integer is infinite. Now also there is the third or the fourth example of sets called power set, where we have all subset of a set like A, denoted by P of A, is called the power set of A. And this satisfies the condition where we have A has an element, small a and small b, then the power of A, which is the combination of all elements in this set. It will be phi, because phi is an element of any set. It will be the small a alone, it will be b alone, and it will be a and b together, because a and b is a subset of that set. So the cardinality of any set based on this could be 2 to the power n, where n is the number of elements you find in any set. There is a famous concept we use in computer science when we deal with computer databases, which is a tuple, which is a record, a row of data. Normally we call it a tuple in databases. Why? The reason for that, because we are talking about an ordered number of elements in a set, where we have A1, A2, up to AN. And normally this is what you find in any database. You will find, for example, if you have a student database, you will have a student table, and in that table you will have one single row where it contains the student number, student name, student last name, student email, and then student grade in computing fundamentals 1, which is 40, which is a pass. Now, when there is two tuples are equal, if and only if there is a corresponding element are equal. And this is what we call in computer science inner join, where there is exact match between the elements of the first row with the element in the second row. Sometimes we use the concept of ordered tuple, normally with key value pair. For example, in JSON file and XML. So you will find an order pair where you will have, for example, first name, Basil, second name, Magabi, email, something, and so on. You will find an order pair where we have a key and a value. And we call a tuple is an ordered pair, A and B and C and D are equal if they satisfy the following relationship. If and only if A equals to C, B equal to D. Now, you need to find an exact match between the keys and the values. And this is how JSON processing or parsing normally works. Final operation of sets, which is very important to focus on, which is the Cartesian product. What we mean by Cartesian product? The Cartesian product of two sets, A and B capital, donated by A multiplied by B, is the set of ordered pair AB, where A now belongs to A capital and B belongs to B capital. In this case, you will take all the elements A and B where you satisfy the relationship. So the first pair should be the first pair of the result of the Cartesian product should be small a with a small b, small a2 with a small b2, and so on. Now this is what we call in databases natural join, because we do just Cartesian product between two tables and we basically blend them together. All the elements of the two sets are blended with each other. Now take an example. If you have an A set capital where we have the small element A small b small, and we have another set called B capital, it has 1, 2, 3 as an element. Now let me take one by one between both sets and I will just combine them in an ordered pair. So I will take A from A capital, 1 from B, A from A, 2 from B, A from A, 3 from B, B from A, 1, and so on. So B1, B2, B3. Now the last information you will find about Cartesian product, if you have a subset called capital R, this subset from the result of the Cartesian product A multiplied by B is called a relation from the set A to the set B, which is basically what we do in databases as normalization. First normal form and second normal form is basically used in computer science to filter and to just tune the data in the table using the definition of the Cartesian product. So once you think about Cartesian product, you will find about a small subset, A capital 1, A capital 2, and so on, where we have A small 1, A small 2, all the way to A of n, where A of I now is an element of A capital of I for loop, basically from I equal 1 to n. So the Cartesian product of the sets from A1 capital to A of n is the set of ordered tuples where you have now ordered tuples, not ordered pair. Okay? Where we have A1, A2, A of n, where A of I basically a loop from I equal 1 to n. Now the result from this will be simple to see it in the example. So let me explain the example first, then we'll go back to the actual definition. So if you have A multiplied by B multiplied by C, where A is 0, 1, B is 1, 2, and C is 0, 1, 2. Now take every element from every set and just blend them with each other. So I will take 0 from A, then 1 from B, then I will take 0 from C. Then I will take 0 from A, then 1 from B, then I will take 1 from C. Then I will take 0 from A, 1 from B, and then I will take 2 from C. And so on. So I will match every element in A, B, C with every other element in the other sets to make a tuple of data where we have different formation from a mix from each element in the set. The last thing before we start our activity is basically if you have a predicate like B capital, which is basically a mathematical definition, a mathematical description describing a rule, and a domain D, and domain D could be the universal set, the big set that contains everything in universe. We define the truth set of B capital to be the set of elements in D for which P of x is true. Now here we are talking about P of x as a function that should be true in terms of logic. So the truth set of P of x is denoted by an x is an element of D where it satisfies the function P of x, or it is a true value when the function P of x exists. As an example, P of x, where the domain is the integers. Now, if P of x is an absolute value of x, the positive value of any number, equal 1, then the set minus 1 and 1 both satisfy the rule. Both satisfy P of x. So those two values make function P of x true. Now, let us do this activity together. Now, with set operations, we have a specific operations that we can use with sets and the elements of the sets. So we will speak about how we can make a union between two sets, how we make intersection, and how we can complement a set and find the difference between two sets. So with propositional calculus and the set theory, both are basically an instance of an algebraic system which is called Boolean Algebra. It is the same that you use in logical design, in the digital circuit of the computer motherboard. So the same operator you would use in the set theory are corresponding to the same operator that you use in a propositional calculus, which is an algebra. So as always, there must be a universal set U that contains every single element that you can consider, or you can sense, or you can think about. So let us first take what we mean by the union of two sets. The merge between sets, two sets, means that there is an element called X. And in this case, X is an element of the set capital A and, or is an element of the set B. So any element in both sets will be merged, will be taken into the union. So there is a union between sets. This means that you merge them and you make a larger set of both sets. So if you have an A and B capital sets, the union will be denoted by the simple upside down horseshoe, which is A union B. Now the mathematical definition of it, as we said, X is an element of A or X is an element of B. Now when you change the OR to AND, it will be an intersection. It will not be a union. Take for example what you can see now as an element of the set A, 1, 2, 3. Make union of this set with another set with the element 3, 4, and 5. The result of this merge, the result of this union will be 1, 2, 3, 4, and 5. Now, you might be asking, 3 appears in both sets. Do I need to duplicate it? No, you don't. You don't need to duplicate it because this means that 3 is an element of B and element of A, and it will appear on the union between A and B. Now when you think about intersection, you are thinking about a common factors or a common elements between two sets. So basically, you can define it by mathematical definition X, where X is an element of A and it should be an element of B. And we know what AND means. The truth table of AND means X should be true as an element of A, and it also should be true for an element in B. As an example now, the same sets that we just merged in the previous example, now let us find a common factor between them, a common element. You will find that 1 is in A but not in B, 2 is in A but not in B, 3 is in A and it is in B, so this is a common element. So this is like the result of intersection. 4 is not in A, but it is an element of B, and 5 is not in A, but it is an element in B. Now, the same. Take another example. What is the intersection between the set 1, 2, 3 and 4, 5, 6? There is no common factor. There is one single common factor between them. We said that phi, the empty set, is an element of any set. So phi is the only element between them. Now there is another type of relationship between sets called complement. It is the same when you take a binary code and you take the complement of the binary code. So what we mean by a complement? If we have a set A, then the complement of A prime, is donated by a dash, that little prime symbol there, is the set where you have the universal set, everything we could think about, minus that A. This is what we mean by the complement of A. So, in this case, the definition of the complement, X should belongs to you, and by the definition, everything belongs to you, where now this X should not be an element of A. So if you now I will define what we mean by you, because you could be defined or could stand for any set. If you now donate the positive integer less than 100, what is the complement of the set where X is greater than or equal 70? This means anything greater than 70 is already an element of the set A. The A complement is basically anything less than or equal 70. So you take U minus A. And when you describe it in the Venn diagram, you will see that the big square stands for the universal set, and now you represent the set A, and everything outside this circle, inside the square, is basically the complement of A. There is another type of definition, which is called the difference between A and B. Now, don't mix the difference with intersection, because intersection is a common factor. Now here we are looking for A minus B, which contains the element of A that are not in B. So you always take it left to right. So you think about an element which exists in the set A but not in B. So the difference between A and B is also called the complement of B with respect to I. Now, how is this happening? You could simply say now, U is basically the set or the element represented or existed in set A, and then you do the complement of A, which will basically result on B in respect to A. Now, A minus B, you can define it as X, where X belongs to A, and. Now, the AND condition is important here because X should not be an element on B. So when you speak about it, imagine that you have a C, or you want to represent it in a diagram. You will find that a set A and there is a set B. Now make the intersection. The intersection will be what? Will be the common factor between them. Now anything outside this intersection, outside will be basically applies to the rule of the difference. So including the intersection, the common factor, because the common factor between A and B is basically not satisfying the rule. The rule said, I don't want an element to exist in B. But any element common between A and B is exist in B, so we cannot take it. So anything outside this, which is the A in the blue color you see here in the diagram, is basically the difference between A and B. Now with cardinality, where you have a union of two sets and you want to do the cardinality, you could simply use the same laws of logic, where we have the cardinality of A union B is basically the cardinality of A plus the cardinality of B minus the common elements between A and B, the intersection between them. And you can verify this by the diagram. So let A be the math major in your class and B will be the CS major. You need to count how many numbers of students who are either math major or C majors, and the number of math majors and the number of C majors, and subtract the number which is basically the result of the join between CS, math and major. We will go back to this principle again, but this is just to give you the sense what we mean by cardinality. Now let me give you few examples so you can practice all these relationships by yourself.